So reminders here, guys. First off, I did post the unit exam review package in Google Classroom yesterday, so you now have access to that. Okay, it's a little bit different than the previous two. Okay, I'm kind of trying to wean you off of it all being my stuff and being more your stuff. Okay, so there's no practice test, but there are a bunch of like old exam questions as part of the review package, but there are no multiple choice ones on this. Okay, lots of just problems with the answers there, so you can check them as you go. Okay. Reminders of other due dates. Obviously, the work lab is due on Monday, so make sure you've got that ready to go. And then your unit exam is on Thursday. So key things for the physics units, right? We started off and we talked about the types and forms of energy. So we talked about thermal energy, we talked about mechanical energy, we talked about nuclear, solar, chemical, electrical, all that kind of stuff. So expect that there'll probably be some multiple choice questions about identifying a type of energy. So if I had a question like, a skier is skiing down a steep slope, which type of energy would they have? A, chemical, B, mechanical, C, solar, D, nuclear. Hey, it would be that easy, but it'd be something along those lines. Just being able to identify the kind of predominant energy type. Okay. We also talked about systems, the three types: open, closed, and isolated. Okay. Open systems exchange matter and energy with their surroundings, so you are an open system. Okay. A closed system only exchanges energy with its surroundings, so that could be like something sealed in an airtight container. And an isolated system is pretty much theoretical and would not exchange either matter nor energy with its surroundings. Okay, and then we talked about thermodynamics. The first law is the law of conservation of energy. Okay, the second law tells us that energy flows from hot to cold, high to low. Okay. We talked also in that about heat engines and heat pumps. Okay, so like a jet engine was a heat engine, and your refrigerator or air conditioner was a heat pump, and how they work. Right. We also talked about perpetual motion machines and why they can't exist. Okay. I would say that there's a few multiple choice items about thermodynamics and perpetual motion machines. I would be able to explain why the laws of thermodynamics forbid the existence of one of those. Okay. Questions so far? Then we talked about scalars and vectors. So definitely know which quantities we have talked about are scalar and which quantities we have talked about are vector. Okay, if something is scalar, it has only magnitude. If something is vector, it has magnitude and direction. Okay, so speed, scalar. Velocity, vector. Okay. What are some other vector quantities? Displacement. What else? Time scale. Acceleration is vector. Okay. And even though we haven't done much with it, force is also a vector quantity. We never treat it that way because we always use it as part of the work formula, and work is scalar, so it doesn't really matter in that regard. Okay, but we got these ones here. Okay, distance, time, energy, and work are all scalar quantities. Okay, and then those are our vector quantities there. And on that same day, we introduced V equals D over T. So there will be some V equals D over T questions, but they will be multiple choice. Okay? There's just not enough to do with a simple V equals D over T question to make it worth a 3 or 4 mark written response question. Okay? So there'll be multiple choice. as will the scalar and vector quantity. So I could have a question that would say, which of the following is a vector quantity, A, B, C, or D? And you have to identify which ones. All right, so far we haven't had much in the realm of written response stuff. It's mostly all been multiple choice, because this is kind of the introductory stuff, the basic stuff. Okay, and then graph. This was an area where we struggled a little bit. Okay, so you need to understand there's a fair amount of graphing on this exam. There are some multiple choice questions where you have to interpret the graph. So I show you a position versus time graph with a diagonal line, okay, pointed upwards, right? And I ask you, what is this graph showing? A, object accelerating, B, object not moving, C, object traveling forwards at a constant velocity, D, object traveling backwards at a constant velocity. Which one is it? C. Okay, the position versus time graph, and it's just a straight line. That means the position is increasing at a constant rate. That's constant velocity. Acceleration would be a curve. Okay, on a velocity time graph, that would be accelerating. Okay, those are the kind of things we need to be able to interpret from a graph. Okay, and be able to use y equals mx plus b. Right, so I could give you something like this, right? A velocity versus time graph, and say in a written response question, calculate the total displacement. How would you do that? Find the area under the line, right? So I find the area of this box, the area of this triangle, the area of that rectangle. Triangle, that's a triangle. That's 3 seconds. Okay, so you find all those areas. Is one of them negative? Is that important?
Yeah.
Yes, if I ask for the total displacement, it is. What if I ask for the total distance? Then it wouldn't be. Okay, that's something to watch for. Okay, that's that whole scalars and vectors thing, and understanding when direction is important and when it isn't. Okay, could I also ask you to calculate the average acceleration between 2 and 5 seconds, let's say? Okay, how would you do that? Right. Okay. What if, instead of the graph looking like this, the graph now looks like this, and I give you that. And then I say, what is the acceleration of the object over the whole trip? .5 meters per second squared. Because on this graph, is that showing acceleration? Yeah, it's a velocity versus time graph, right? And we know that the slope of the line on here would be meters per second divided by seconds. That's meters per second per second. Okay, so the slope of this graph would be equal to acceleration. How many marks would that be out of? Absolutely. Okay, only 1 mark. Right? If you did this and did the whole calculation, would you get it right? No. Here's why you wouldn't get it right. I would make sure in building the graph that your last point was nowhere near the line. Okay, so if the graph is showing this, it would show also all the points used to make the line. Okay? I would make sure that last point is either way above or way below the line. Now, if I use this, I would use that point and like this point or this point, something, but it wouldn't give me the right answer. Okay? Because the slope of this line and the slope of that line are different. Okay? Remember that when they give you the equation, it's using all the points, not just the first and the last. This formula uses the first and the last, which is fine for the first graph we had, but it's not good for this one. Okay? Everybody all right with that? Is that exactly what you had to do in the Need for Speed lab? It is. Okay? I'm not going to ask you anything different on your unit exam. Okay? Make sure you look at those two labs. The stuff you had to do on there is the stuff you're going to have to do on the test in terms of graphing. Okay? I'm not going to pull something out of a hat that you've never seen before and ask you to do it. That's not fair. All right. Now, here's the other thing to watch for. If I give you a graph like this and I give you the equation for the line, I will have in the question, using the graph and the equation for it, do this. So, should you use the equation? Okay, remember that. Okay, because a lot of people won't. Okay, they just go off and do something else, even though the question says, here's how to do this question. People go and do it a different way. Don't go do it a different way. Okay, it's saying do it this way. That means I'm trying to test this skill. I want you to demonstrate this skill, not something else. All right, everybody with me there? So always be on the lookout for that. Lots of times, the question will say, please do this question this way, recognizing there may be more than one way to do it, and this is the skill we're trying to assess. Okay. All right, what if I asked you to calculate the total displacement? Right? So I would have to do 3 calculations here. Okay? I would have to calculate the area of this box, which would be 2.7, the height of the box times whatever the base of the box was. I would have to calculate how tall the triangle is using this formula and using, let's say this is 10 seconds here, okay? Using x is 10, find the height of the triangle, and then find the area of the triangle, add them up. Okay? Same thing you had to do, excuse me, on your Need for Speed lab. Okay, so that's with your velocity versus time graphs. Now, we also dealt with position versus time graphs. So, I could give you a graph that looks like that. And say, calculate the average velocity over the whole trip. Okay, so this is a position versus time graph. Okay, and I want to calculate velocity. How do I calculate velocity? Okay, and from a position versus time graph, I find displacement by going change in position over change in time, which in other words would be like if this was a straight linear graph, would be the slope. Okay, so here's my final position. There's my initial position divided by the total time. Okay, I've got my average velocity. Okay with that? What if I asked you for the total distance traveled? I add them all up. What do I add up? Okay, the distances of each one. Is that an area calculation or is that a looking at the points calculation? Looking at the points calculation. Okay, so I would figure out how far I go here. How far do I go here? 0. How far here? 0. Right, so I just need to go here, here, and here, and then add them up. Okay, remembering that vector doesn't add up. Okay. I give you a position versus time graph. It looks like that. What's that object doing? Moving backwards at a constant velocity of Negative 2.5 meters per second. Okay, again, not accelerating. That's our gut reaction, okay, because we see something changing, but here, what's on this graph that's changing? The position. Okay, but the position is changing at a constant rate. That means constant velocity. In this case, that constant velocity is 2.5 meters per second backwards. Okay.
Would this be squared or not?
Would what be squared?
Only said 2.5 meters per second.
No, just meters per second.
Okay.
Right? It's only squared if it's meters per second squared, and it's not actually the number that's squared, it's meters per second per second.
Okay.
Okay. So on a question like this, I could also ask for, you to use y equals mx plus b. So I might say something like, how long would it take the object to reach a position of negative 20 meters? Okay, what are you being asked to solve for? How long will it take the object to reach a position of negative 20 meters? What are you being asked to solve for? X. Okay. And then I could also say, calculate the position of the object after 100 seconds. You're looking for Y. Okay? So little things like that, exactly the same thing you're asked to do on your graphing lab, okay, on position versus time graphs. Again, I'm not going to ask you to do anything surprising, just all the stuff we've done in class multiple times. If there's one thing that you should practice more than anything else, it's graphing. There's more marks on this test on graphing than anything else. Okay? Second most important thing would be work energy theory. Okay? Third, conservation of energy. Fourth, acceleration. After that, they're all kind of the same. Okay? All right. So then, acceleration. Should you expect to have to solve some problems using A equals VF minus VI over T?
Yeah.
Yes, definitely. Okay? They will be no different than the ones that are in your workbook, okay? Or any of the examples we did in class, or any of the ones that were on your quizzes in class. Okay? They will all be like that. Okay, and then work energy theory. Like I said, probably the second most important thing on the test. There are two written response problems about work energy theory. One where there's a change in potential energy, and one where there's a change in kinetic. Exactly like the many examples we did in class. Now, in your digital workbook, there are still a bunch of work energy theorem problems. We didn't do any of them. Okay? But you've got them there, and the answers are in there. So, not a bad idea to maybe practice a few of those in preparation for your unit exam. Okay? I just made up a ton of examples, and we just went over the ones that I made up. Okay? We didn't even get to the work. Okay, so that stuff should all be fairly fresh in your mind. Okay, if I have a question and the givens are that the velocity changes from 20 to 0, what kind of energy is changing? Kinetic. Okay, if I talk about how the height is changing from 20 meters to 35 meters, potential energy is changing. Okay, it's so patterned, guys. We just got to practice that pattern so we know what to do. Right? Then the stuff that we talked about yesterday, conservation of energy. We're going to be doing a lab on that on Monday. We're going to spend all of Tuesday working on conservation of energy and probably a little bit of Wednesday. And then on Wednesday we'll talk about efficiency just because it's so minor. Okay? And basically I only need to tell it to you so you can do one of the analysis questions on your lab. Okay? Like that's basically all there is to efficiency. All right, so for the conservation of energy question, it's going to be a lot like what we were looking at yesterday with the falling rock, except it'll have all four kinds of energy. So it'll have initial potential and initial kinetic, final potential and final kinetic. Okay, so there'll just be more things to move around, but fundamentally it's the same as what we were doing yesterday. Okay, so that will be in the written response, okay, being able to do questions like that. And then efficiency. Okay. There's like one multiple choice question on efficiency. Basically, you just need to know what it is. Okay? There is a formula for it, and it's easy to use, but it's not something you need to spend an hour studying, that's for sure.
So it's not going to be a ring response.
No.
Okay.
Like I said, basically I teach it because it's in the curriculum and it's important for you to know what it is. In terms of how well you can use the formula, I'm not really that concerned about that. Okay? Efficiency is more of something to be mindful of rather than to do calculations for. So, know it well enough that you could justify changing out all the light bulbs in your house from incandescent to LED because they're more efficient. Yeah. All right, so we're looking at, I better double check that. I think I changed. No, 20 multiple choice and, I changed that question, but it's still 7 questions. Okay, yeah, and there's 7 written responses.
Is the formula for efficiency, is it EFT? Is that what that says? Over.
EFF, sorry, that's supposed to be EFF, is work out divided by work in.
Okay.
So it's the input energy, or the output energy, or the work done divided by the energy you put into it. Right. So if you're looking at like an incandescent light bulb, it uses 60 joules of energy every second, but only puts out about, let's say, uses 60 watts, that's 60 joules per second. Probably only puts out about 4 joules worth of light. Okay, so it's not very efficient. Whereas you can replace a 60-watt incandescent light bulb with about a 6-watt LED. Okay, because an LED bulb puts out 4 joules or 4 watts worth of light and only uses 8 watts worth of power. Okay, it's way more efficient, right? It's like 75% efficient versus 25% efficient. It's just way better.
And did you say that, like, for graphing, there's going to be some written response and multiple choice?
That is exactly what I said.
Okay.
Because that is the truth. All right, so in the multiple choice, like I said, 20 questions and the topics in there. Thermodynamics. Okay, so like read your notes from day 1. There's a lot of like quoted almost definitions from day 1. Okay, types of energy, the systems. Okay, V equals D over T, scalars and vectors. Graphing. So if we go back to acceleration, I think I must have deleted it or erased it when I wrote in this stuff. But this word is right at the very top of the notes on acceleration. You need to know what inertia is. It's the remember I said this desk will just sit here as long as nobody bumps it, right? That was inertia, the tendency of an object to keep doing what it's doing. To accelerate something, you have to change its inertia. Basically, that's all you need to know about it, but it's just a term that we only briefly discussed. Okay? So you just basically need to know its definition. There's no calculations or math or anything. Some acceleration in the multiple choice. Some energy, work in energy, and an efficiency question. That's basically the definition of efficiency. Okay, for the written response. Question number 1. Graphing. Question number 2, acceleration. Question number 3, graphing. So there's one of each type on there. One position, one velocity. 4 and 5, work energy theorem. Six, law of conservation of energy. And 7 is an acceleration problem, but it's got a trick. It's kind of one of my see how well you really know this kind of questions. Okay, any questions from you guys? Yes.
When you talk about like law of conservation of energy, are you talking about more like the equation or
The equation.
not like
In
explaining
the multiple
it?
choice, I'm talking about explaining.
Okay.
In the written response, I'm talking about a problem.
Okay.
Yeah.
And then when you say like the more like tricky acceleration, like is it still an equation that you have to solve?
Still an equation question. Yeah, it's still a problem to solve, but it's the context is a little trickier. We've done ones like it, but it's a trickier context. Okay. What else, guys? Okay.
Do you have to know all those different like men who contributed to like physics and energy stuff? No? Okay.
I don't think there was a single question about a person on there.
Okay.
And like how many points is there in the test?
65. Okay, so there's 45 in the written and 20 in the multiple choice.
And we're getting the basic, just like formula sheet from the back of the periodic table.
I have put all the formulas you will need on the front page of the test. Okay, when you're studying for this, okay, I'm going to kind of tell you the same thing I told you the other day when we talked about time management, okay? Do this in small chunks, right? Do a couple of work energy theorem problems. Do a graphing problem. Do a acceleration problem. But like separate them, okay? Do a couple of work energy problems and then walk away. Okay, take 10, 15 minutes, do a couple of them, then walk away, do something else for a while, come back and do something else. Let your mind process what you've done so that it can commit it to memory. But if I'm doing 5 work energy theorem problems, then right away I'm going on to 3 conservation of energy problems, and then I'm doing 6 graphing questions, and I just sit down and do a marathon 3-hour session, okay, I'm not going to remember it all. And I'm going to start to confuse what I do in each of those problems with what I do in other problems, and that's not going to be good. Okay, you want to work on a skill, practice that skill, move on to a different skill. Okay, chunk it up, right, so that it's one thing at a time. Take breaks. It's really important to take breaks. I mean, take breaks. Don't like always be on a break, but like take breaks. Okay, that's still a good thing. Okay, get away from it. Do something else for a little while. Okay, and make sure, guys, that this is very much like chemistry. It's about showing me what you know. There's only 20 multiple choice questions here. Okay, That's not very much. Okay? There's not much in the notes of this unit. Okay? This is mostly about being able to demonstrate to me your understanding of something rather than being able to read and regurgitate, okay, like it was in biology. Right? This is about showing me, I understand that this problem is a work energy theorem problem, and it's about a change in kinetic energy, and I can set it up and I can solve it. I understand that this is an acceleration problem, and it's a falling object, so acceleration is 9.81 meters per second squared, and I can set it up and solve it. Okay? That's the bulk of the test. Okay? Here's this graphing question. I remember how to use y equals mx plus b, or I know how to calculate displacement from the velocity time graph. Demonstrating those things. Okay, I understand that that's what this kind of question is, and I know how to do it. Right, so that's what you really need to work on. Just reading through your notes for hours on end is not going to help very much. Okay, I'm not saying it's useless, but I wouldn't spend that much time reading through my notes. I go through them once or twice. Okay, that'd be it. Then I practice. All right, well, you still have a bit of time here, okay, about what, 15 minutes or so. So if you want to look at the unit exam review, or do we want to do another conservation of energy question?
We do graphing questions.
I don't know if I have any more. I kind of used up all my examples because I made like 20 more examples this year. I don't have any new ones. I don't have any more new ones. Okay, why don't you guys work on something? I'll try and build one of each. Okay, it's going to take me a while because I got to build the graphs. I don't have them unless I. No. Okay. All right. So here's our two graphs, one of each. Okay. What's the velocity of this object?
2.7 meters per second.
2.7 meters per second, positive 2.7 meters per second, but I'd accept 2.7. It should be positive though, because I asked for velocity. Okay. Second part would be calculate the position of the object after 25 seconds. Okay. And this question would also say, using this graph and then in bold-faced, italicized, and underlined print, and the equation for it, solve the following questions. What's the velocity? B, what's the position of the object after 25 seconds? All right, so what are they asking me to calculate? Y, okay? 25 seconds is a time, okay? Time's on the x-axis, and that's something we have to be able to identify, okay? If it's asking for position, position is on the y. I'm looking for a y value, okay? So y equals 2.7 times 25 seconds. They gave me the x value plus 0.309. All right, so 2.7 times 25 is going to be what, 68?
Yeah, 67.809.
67.809. Okay, plus 0.309. Okay, so 2.7 times 25 plus 0.309 gives us 67.809. Okay, that would be the position of the object in meters, okay, positive, after 25 seconds. Right? Were you asked to do that on your lab? That's question number 2 on your lab. Okay, all right. Part C. How long will it take the object to reach a position of 85 meters? What am I asking you to find? X. How long? That's time. Time's on the x-axis, and they said 85 meters. That's a position, so they gave me a y value. So y equals m times x plus b. I got to solve for x. What do I move first? B. So y minus b divided by m equals x. So that's going to be 85 minus 0.309 divided by 2.7. All right, so it'll take 31.4 seconds. Everybody okay with that? So again, nothing I didn't ask you to do on your lap. Okay. Any questions on that one? Okay. Let's say on this one, what's happening during part B? It's accelerating.
At a constant
Constant speed. Rate.
It's accelerating positively. No, it can't, this is, because you guys say this every time I ask. You always say accelerating at a constant velocity. You cannot do both. Okay? You are either traveling at a constant velocity or you are accelerating. You cannot do both because acceleration by definition is a change in
speed.
velocity or speed. So it cannot be constant while doing the other. Okay? So make sure you get that straight. Okay? So in part B, we are accelerating positively or accelerating in a positive direction. What are we doing in part C?
Accelerate. Oh, C?
Part C.
Moving at a constant.
Moving at a constant velocity. Okay? And for D?
Accelerating negatively.
Accelerating negatively. All right. In fact, you could also say, and you'd be correct in saying this, coming to a stop. All right. It didn't do a very good job of picking the numbers here, but this is -4 right here. Okay, and this is 9 up there. Okay. Calculate the total displacement of the object. How many shapes are there? 4. 4. Okay, that triangle, that triangle, that rectangle, that triangle, 4 shapes. Okay, base times height over 2 for the triangles, base times height for the rectangle, and what do you need to remember about part A? It's negative because I asked for displacement. All right, so that area is going to be -4 times 2 divided by 2. So it's just going to be -4. Okay, this one here goes from 2 to 5 and goes up to 9. So 9 times 3 is 27 divided by 2. It's going to be 13.5. And then that one's 2 seconds. It's 18. And that one is also 2 seconds. It's 9, yeah. All right. Add them together and you got your total displacement. Again, keeping in mind that part A is negative, and that matters. All right. I'm not going to ask you to do anything harder than that on your unit exam. Okay. All right. I need to wipe down your desks.